A review of exam 2 in dynamics. So let's do it in real time here. Here is, I think this might have been the one that I was calling version A, I think, right here. So these are the numbers. The other two versions, B and C, will have slightly different values for right here. So I should describe my thought process when trying to solve this problem, but I look at this thing and I can picture what's happening. Is this thing is accelerating, and therefore a cable with a ball that would normally be hanging vertically is now moving over, hovering over to the side, right? Can you picture that? Maybe something hanging from your rearview mirror, right? And you're accelerating so much that it starts to kind of point backwards, right? So that's the thing that happens. And from this, I can estimate the acceleration of the entire thing, because both of these are accelerating at the same rate. So I'm going to focus in on this piece and draw an FBD and IBD. And I can't emphasize how important it is that you make an FBD and IBD when you're doing Newton's second law. So I recognize this is a Newton's second law problem because it can't really be a work energy problem because we don't know anything about two different states. So we don't know, like, if something had moved a distance, or we knew something about, like, when it's gone this distance or something along those lines, that would be indication for work energy. If it was like after this amount of time, or we were trying to find the time, there's often what would be like an impulse of momentum. But this is just an instant in time, so it has to be Newton's second law. So first off, I'm going to draw this tension because I've cut this cord to be able to see this thing. I also have the mass, and this is going to be the mass of B times G. Right up here is going to be the same angle as that angle. And then this thing is accelerating in that direction. So mass times mass B times the acceleration. And that's the acceleration of the entire thing. I could say the acceleration of X if I wanted to. That's fine. So I'm going to take the summation of the forces in the Y direction. Mass times acceleration in the Y direction. But I know that this thing's not moving up and down. It's not going to move at a different time, so at a different location, whatever. So I take Ft. I'm going to take the cosine of that theta right there, and we have that angle minus the mass of B times G equals 0. So I could find the tension right here, right? So if I take MB G over cosine of theta, which the mass of B is going to be 5. 9.81 is the acceleration to gravity, cosine of 20 degrees. And now I have 9.81 times 5 divided by the cosine of 20. And I get that it's got a tension of 52 point, really 20, really, right? And those are in newtons. Now I got the summation of forces in the x direction, mass of B times the acceleration in the x direction. And I just have Ft, let's move this up a little bit, Ft times the sine of theta is going to be equal to Mb times Ax, right? So I could find the acceleration in the x direction is going to be at Ft sine of theta divided by Mb. And truth be told, I could have left this as symbols, and I would have found that the angle or the acceleration I could have found without the mass. Like the angle wasn't dependent on the mass, kind of sort of a surprising thing, but we would have found that. So you get the 52.20 in the sine of 20 degrees and divided by our 5, I believe, right there. So we get the acceleration in the x direction. So 52, going to go to the sine of this times it and 5 divided. So we get the acceleration is, it looks like, I can't read my little, kind of dim in here, 3.57, call it 1 meters per second squared, right? How did I do on that one? Yeah, I got it right, okay. And now I want to try to get the I want to get this unknown force. So what I'm able to do here is another FBD and IBD pair equal to each other. Here's X and Y. We're going to have a normal force, Fn, and I could call it Fna if I want to. I'm going to have a friction force, Fa. Here's the force that I want to find. I'm also going to have a mass times gravity force, right there, the weight of this thing. And I have, lastly, I have a tension right here. Right, because I've taken these things separately and I cut it right there to be able to see the one up above. That's going to be helpful to me. And let's see, and this is only going to have mass time ma acceleration in the x direction. So I'll take the sum of the forces in the y direction, mass times acceleration in the y direction. But I know it's not moving anywhere in the y direction. So what I have here is I have Fna. That's the reason why I'm doing this part of it. And let me see, I had to put that angle right in there too. I'm going to have a minus Ft times the cosine of theta right there. And then I'm going to have a minus mg equal to 0. So I can find my Fna. And that's simply going to be that 52.20 that I had before, times the cosine, times the cosine of my 20 degrees, and then minus my mass of the whole thing, which is 30 kilograms, times 9.81. And it shouldn't be a minus because they're both minus over here. They come back onto the other side, so they should be plus. And so here's our 52.2, and my cosine of 20 times, and then my 30 times 9.81. Add them together, and I think I get, looking at the 343.4 newtons. And then I know that the friction here is going to be the coefficient of friction times my normal force. When my coefficient of friction was 0.2 and my normal force 343.4. So 0.2 times that, and I get 68.67 newtons. So if I go, the sum of the forces in the x direction equals mass times acceleration in the x direction. I'm going to have, I'll put this F there, subtract out Fa. I'm going to subtract out a little bit of this right here, because it's going to be the sine of theta. Nothing else in the x direction equals to MAAX. F is going to be equal to, that MA is 30. The acceleration is 3.571 plus the friction force, 68.67, plus the tension force of 52.20 times the sine of 20 degrees. And I will get, let's see, 52.20, 20 sine times, add those together. I'm going to multiply that by 30, add it, and I get 193.6 newtons. So that's my answer. 194 newtons. Let's see how long it took me to do that. All right, about 9 minutes, call it 9.5. Okay. Let's get back up to here. Let's do problem 2. All right, so here we have this pendulum, right? And we don't know the angle. We do know the length of it, and we do know how much this is going to weigh. And what happens is we release it from here, and it swings. And when it gets to this long position, it hits this little bar, and then this lower part of it starts to swing up, and it pauses right there, right? So it's released from position 1, it connects with the horizontal, and then pauses at 2, which is x times L below there, where x is multiplied by the length, so it's at 0.6. So we want to know the angle at which the ball is released. I saw several people just jump into this with geometry, and that's incorrect, but I didn't, wasn't harsh on that, although I kind of thought that maybe you should be applying dynamics and not just trying to come up, you just kind of jump to a conclusion without like going through why it would be so. And the reason why it's going to be so here, right? The reason why we would be able to do some geometry right in here. So let's see. I'll actually draw it the way it's going to be actually done. I'll click right there, right? So here is the thing. Of course, I didn't draw it very well here. I'll try to draw it a little better. There you go. This is state 1, and this is state 2. And I kind of wish I named it state 3, but that's all right. I'm going to name this state 1.5. That's what I did. And I'm going to make this the datum. It's just going to be easier for me to make that the datum. So this distance right here, I'll call that maybe y1, and this distance right here is going to be y2. All right, so I write out my equation, and just so you know, it's really good idea to write out the equations for these kinds of things. You get all kinds of partial credit for having done that. Okay, so KE1, 0, right? Starts out at 0. PE1, well, there's no springs, so the only thing that I'm going to do here is it's going to be Y1, right? So it's going to be the mass times gravity times Y1. Well, what is Y1 from right here? Well, first off, this is L, right, from here to here, that entire length. So if this is theta right here, well, Y1 is going to be mg, it's going to be L times 1 minus the cosine of theta. We had a problem, an example problem that was like this, where we had that kind of geometry thing going on. And then there's no work being done between states 1 and 2, no losses. The KE2 is 0. It pauses right up here. And so PE2 is going to be mgy2. And so that's going to be mass times gravity times, where this is xl, right to there. So this must be 1 minus xl, or L times 1 minus x. Plug all those guys back in there, and we get 0 plus mgl 1 minus cosine of theta plus 0 for here equals 0 for kinetic energy plus mgl 1 minus x. And you can see that the mass is going to cancel out, gravity is going to cancel out, even the length is going to cancel out. So what we're left is 1 minus cosine of theta is equal to 1 minus x. And maybe I should even point out to you that y1 had to be equal to y2. That had to be equal to that. So even though it's kind of deceptive, by the way, I didn't make this drawing, so whoever created this drawing sort of made it deceptive, but this has to equal to that. And maybe that's the, I didn't take off points when you didn't do all of this, simply because I was thinking, well, you know, when I saw one of the students who did it, I was like, they could have just knew that and didn't write it down, that y1 had to be equal y2. And so, because I did it for one student, I did it for all of them. So it's a sort of a lenient grading thing. I wanted you to do this. That was the whole point of the problem. But I went ahead and was, I don't know, call it merciful if you want. But anyway, the ones are going to cancel out. So all you really have is the cosine of theta is equal to x. So theta is equal to the inverse of x right there. Or in this case, that x was 0.6. So we got a theta equal to 0.6. Let's see what the inverse cosine of that's going to be. 53.13, right? So it's actually like, isn't that a right triangle? I mean, isn't that like the 3, 4, 5 triangle angle that we would get? I don't know. Anyway, so there's part of this. And now the next thing that we're going to do, we want to get the tension of the string just after it touches the bar. Well, my thought process in this one was I asked rectangular coordinates for Newton's second law in the first problem. So I wanted to ask something that required path coordinates. And I noted that just after it touches right here, the length of the string right here is going to be shorter, right? So this is the point about which it's going to pivot. Therefore, we're going to use the normal acceleration, right? So we're going to, and once again, you need to write this FBD and this IBD. I can't emphasize how important that is in trying to solve these problems. So in this instance, we have a tension. That's what we're trying to find. We have mass times the gravity, but we also have, do we have acceleration in the x direction? No, because this is its peak velocity is happening right there, right? So that's when the velocity is at its maximum. So the acceleration has to be at its minimum, 0. But it is traveling this way right here. It's got an acceleration. So what we need to do, we know I need to write mass times acceleration because this is the IBD, right? Mass times the acceleration in normal direction. And we know that that has to be v squared over rho. Therefore, we have to find the v squared. So what do I do about that? To find that v squared, I find the velocity right here when it's at the bottom. I already kind of have it set up to do it. I just now need to change and find, instead of having it at going from 1 to 2, just go from this one right here. So I called it 1.5. Why not? So I said, and I didn't leave myself enough room for this, but KE1 plus PE1 plus U 1 to 1.5 is KE 1.5 plus PE 1.5. So I know this, and I know this is already 0, right? So I already have, well, let me put them down. All right, so I have KE1 starts at 0. PE1 starts at MGL 1 minus cosine of theta, which I now know. U1 to 1.5 is equal to 0. KE 1.5 is equal to 1/2 M V 1.5 squared. It's the thing I want to try to get here soon. I should have found out the value of that. I'll do it anyway. And then PE 1.5 is equal to 0. All right. So I didn't manage my page very well right here, but I'll keep going with this. So I got 0 plus, and now I go mass, this guy mg, so that mass is, what did I say? Oh, it's going to be 6 pounds. Okay, because it's mg, that's the same thing as saying weight. So I just have to replace this with weight, right? I don't have to put m, I don't have to turn it into mass by dividing by g and then multiply it by g, right? And now the L is through 2.5 feet. And 1 minus the cosine of 53.13, which, no, that's going to be 0.6 right here. It's going to be equal to 1/2 m, which I know is going to be 6, right? 6 divided by 32.2, right in there. And notice that 6 is going to actually cancel out over there. And now we have v 1.5 squared. That 1.5 is not squared, that is squared. So I can actually, and then plus 0. So I could find my v1, I'll call it 1.5. It's going to be 6 times 2.5, boom, times 1 minus 53.13, the cosine minus says 0.4 times that, and then multiply that by 2, divide by 6, multiply by 32.2, boom, and then take the square root of it. And did I get the right answer? I'm not looking at the right page over here in my Excel. let's see. 8.025. And these should be feet per second. So over onto here, sum of the forces in the, we should actually say, by the way, I should probably call this, to be completely correct, normal and tangential. Excuse me. Tangential, normal, right there. I will say in the normal direction, we have mass times acceleration in normal direction. It happens to be up in this case. So we have Ft minus mg, which is the weight. I'll just put the mg, but we could put the weight. Is equal to m times v squared over rho. Rho in this case is going to be 1 minus L, right? 1 minus x times L. So let's just solve for it and be done with it. I'm taking an extra long time with this one. So this mg is the weight of the thing. It's 6 pounds. It goes over to the other side. Plus my 6 divided by 32.2 to get mass. My velocity, which was 8.025 squared, divided by this, which is going that rho, where I said rho was going to be equal to L1 minus x right there, because that's the pivot about which it's going. Remember, because we're just after it touches, so now that's the pivot point about which that normal is going. And so that's the length is 2.5 and 1 minus my 0.6. And so I get a tension in the rope of, let's see, I'll square that number, divided by 2.5, divided by 0.4, multiply it by 6, divided by 32.2. Okay, so I get all of this right here is just 12 plus 6. So I get 18 pounds. And that's my answer. And that's what I was looking for. I was looking for path coordinates in Newton's second law. And I took the long way around, but this is what I expected. So like, see, how long did that problem take me? So I'm up to 22. So that was probably like 11 minutes maybe. All right, so the last one, this was the long one. I had several things going on. Now I only did a conservation of energy in the previous one in Newton's second law, so I wanted to use some work and energy, and I wanted to have a collision, and then I wanted to have impulse and momentum. So that was my desire here to cover these topics, right? So first off, this thing is moving with a known velocity to start with, and and there is friction. So it's going to slow down before it hits right here. So that's our first thing, is we got to figure out how fast is this going. Now, I could definitely skip this part of it right here, but I think it's a bad idea. I really think it's worth doing this every time, even when we're dealing with a direction that isn't going to be moving, right? This is the thought process. This is how we're picking a problem apart, is by making these diagrams. So we have here for this guy, and on A, right here, we have the mass of A times G. We have the normal force of A, and then we have a friction force of A. And there are no other things going on here. And we are slowing down. Now, there's the acceleration of A right there. We are slowing down, so that's the direction that this goes. Might as well set this one up too. This is the other one right here, right? Almost everything being the same. F, N, B, friction force of B, and then mass times B, acceleration of B. I should mention that I'm going to use work and energy because there's a distance, but we could also use Newton's second law here. So we could have found the decelerations in both of these if we wanted to, and then use that distance to be able to find what the change in velocity was going to be from this start to this start right there. We could do that. And the same thing true on the tail end, right? So you could have bypassed this doing work and energy, and you could have bypassed impulse and momentum. So maybe we ought to take that little side journey to find these accelerations, even though that was not my intent right here. And maybe I should have. Sometimes in some semesters I will do it this way, right? But anyway, I thought that's giving stuff away. Maybe I don't know. Sum of the forces in the y direction equals mass times acceleration in the y direction. Here, I'll do it right underneath this thing, and so we get FNA minus MAG, nothing else going on. It's equal to 0. So we get FNA. It's just going to be MG, which is 9.81, which equals 98.1 newtons. So we can get what the friction force is going to be. The friction of A is the kinetic friction times FNA, or 0.2 times 98.10, and we're left with 98.1.2 times 19.62 newtons. And I'm just doing all of that when it's really, I mean, I don't think I would take off points most of the time for not finding it in the y direction. But if you don't do your FBD and you get the acceleration, I'm taking points off every single time because it's incorrect. You're doing the thing that we're here to learn to do, is to do dynamics problems, which requires these diagrams. Do the same thing over here. Once again, this is a big time eater for me as I'm walking through these, but it's worth the invested time. So we get the FNB is equal to mass of B, which is 8 times 9.81. 8 times 9.81, boom, 78.48 newtons. Friction of B is going to be FNB, or 0.2 times 78.48. So we get that it's 150. No. I got 15.9.70 newtons. Okay. As a side note, we could, all right, so here is like, you turn the clock off, we could go, this is the first one, sum of the forces in the x direction, these mass times acceleration, the x direction, boom, right there, and all we really have is the friction force, so you get the negative friction force of A is equal to mass of A times acceleration of A, right there, right? So in this, we get 19.62, right? And both that should be negative because it's showing it as negative, right? So you get negative here equals negative 10, and then acceleration of A. And we get the acceleration of A is just going to be 1.962 meters per second squared, right? Once again, I didn't intend for you to do this, but you could. And then we could also have some of the forces. I'll draw a line in here to make it a little clearer. In the x direction, mass times acceleration in the x direction. But now we can go this one right here, right? And it's just going to be negative FB is equal to negative MB, acceleration of B, right? And so that ends up being negative 15.70 equals negative 8 acceleration of B. And it turns out they're going to be the same deceleration, right? Same, they're both going in that direction right there. So we just divided by 8, and we also get that it's going to be 1.962 meters per second squared. All right. So that, by the way, that chunk of time right there shouldn't count towards my solution time of the thing. This is an alternate approach to it, right? So I wanted this up here, which once again adds to the time that I take for the thing, but it's, I think it's necessary. Now I want to go work in energy. So I'm talking about here is state 1, and I'm going to call this state 2. So the state 2 is just before it hits here. It has moved this direction right here. So I go my KE1 plus my PE1 plus work done between states 1 and 2. And this is only going to be, this is only going to be for box A. Right? Box B is not involved. We're just trying to find out what that velocity is going to be before there. So KE1 is going to be 1/2 mass times mass of A times velocity of A1 squared. Or 1/2, and the mass is 10, and the velocity A1 is 6 squared. So that's what, 36 times 5 or whatever, yeah. So 36 times 10 divided by 2, or 180 Newton meters. Potential energy at 1 and 2 are 0. The work in between states 1 and 2 is going to be negative friction force times d. Right, so it's negative 19.62 times that distance, and that distance I said was 2. So we have 19.62 times 2 right there, or negative 39.24 Newton meters. KE2 is what I want to try to find. Actually, I want to find this right here. So I can put that 1/2 and it's 10 VA2 squared, and then PE2 is equal to 0. All right, so plugging all these back in here, 180 plus 0 minus 39.24 is equal to 1/2 10 VA2 squared plus 0. And I get VA2 is going to be equal to, 180 minus that, multiply it by 2, divided by 10, take the square root. I get 5.306 meters per second. On the side note, I could have also found this with VA2 squared is equal to VA1 squared plus 2 times the acceleration times the delta x that we had right there, right? So we could have found VA2 square root of 6 squared plus 2 times a minus 1.962 times 2, right? That was possible. So I'll take my 36 and my 1.962 times 2 times 2, and subtract them out and take the square root, and I could find that I got 5.306, right? So I got the same thing, either from Newton's second law combined with this kinematics or the work in energy. All right, now I want to have a collision, and didn't see a single person. No, I did see. There were a couple people that did. Okay, I'll take that back. We want to go. I'm going to use the other side of this right here. So let me go to a fresh page right here. So I'm going to go my impulse and momentum. my imp mom, if you will, and write this thing out. We have initial, we have impulse, we have final. So explosion right there. So we have, all right, this way here, MAVA2, and we have this impulse, and they're going to be equal and opposite. Now you could also maybe think about the friction and the normal force and the weight of all this, but the delta T is very, very small that's going on between these two events right here. So we multiply that out through there, and it becomes trivial, right? So even though we might have friction right in there, it's times delta T, and that delta T is very, 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 very small. So it does not influence what these are going to be right here. So this still remains the conservation of momentum. So we're going to have MAVA3 and then MBV, let's call it VB3 right there. So writing out the equation, sum of mass times velocity, well, I'll call it 2 in this case, plus integral f dt, going from 2 to 3 on here. It's going to be equal to the summation of the mass times velocity 3 right in there. So MAVA2 is going to be equal to MAVA3 plus MBVB3. We know this right here. We just found, let's see, the mass is 10. The velocity was 5.306. It's going to be equal to 10 times VA3 plus 8 times VB3. So maybe I'll go ahead and write, let's see, this 10. I didn't need to do that. I go 53.06 is equal to 10 VA3 plus 8 VB3. Explaining it out this way is taking a really long time. So that's going to be equation 1. Then you use the coefficient of restitution. And for this one right here, we're going to go V, let's call it B3 minus VA3 is equal to E times V, make sure we swap these now, A2 minus VB2. We know that's 0. So we get VB3 minus VA3 is equal to 0.7 times VA, which was what we found, VA2 was 5.306. So VB3 minus VA3 is equal to 0.7 times that, and I have 3.714, and that's equation 2. So we take those two equations and combine them together. And let's see, how would I want to do this? I would probably rewrite this one because I don't need to know A3. I need to know VB3. So I'm going to take VA3, bring them over to the other side, and so I'm going to take VB3 and subtract. Yeah, that's going to get minus on that side. That's going to be a minus that side. 3.714. And then put him back up into here. Right? So I get 53.06 is equal to 10 times VB3, right? Times 10 times 3.714 right here, and then plus my 8 VB3. I don't need that parentheses in there. So I can solve for my VB3. So that gets multiplied by 10. And that comes over here, gets added to this right here. And then 8 and 10 get added together. So I divide that through, and I get a 5 point. I didn't look and see. Let's see, move over this. So here, double check there that I got on the right pace for this. 5.011 meters per second. Right. Now the last thing I need to do is I need to find the time it's going to take for this thing to come to an end. Right. Well, I could do it by Newton's second law because I have this deceleration right here. I could do it fairly quickly, but what I wanted you to do, my intent, was that you do another impulse and momentum, but now just on the block B, right? They have this initial MB, VB, 3, plus an impulse acting on it, right? So that's going to be the friction of B times delta T, thing we're trying to get. It's going to be equal to 0 right here. So what we end up finding here is, okay, what is the mass of this guy? He was 8, right? So 8 times our 5.011. I say plus, but it should be minus, right? Because that's going to be minus. So minus, and our friction force was 15.70 times delta T, and that's going to be equal to 0. And I would find my delta T was, let's see, I multiply that by 8, boom, and take 15.7, divide it, and I get that it's going to be 2.553 seconds. Now, also, what I could have done, just notably, is that I had this velocity, and I could have taken, well, this would be the initial velocity, and there's the acceleration, there's the time, and I could have just said that it was going to be equal to 0 times our 5.011, and then plus, and then we had this negative, I think it was 1.962, and that'd be the time. And if we do that right there, we get 5.011 and 1.962 divided out, and we get the same thing, 2.553 seconds. Of course, I meant you to do impulse momentum, but this would, okay, so this is like the side note as well. So I took extra time in my explanation here, but let's see how much time it totally took for all of this. It was 42 minutes. I think I probably wasted 10 of those minutes, at least. Maybe, let's call it 8 maybe, of the thing. But still, what I usually aim for is a 2-to-1 ratio. In our time, we had 75 minutes, so that usually comes out to, what, 37.5 minutes for an exam, and that I should be taking in my time. I think it worked out right around there. So hopefully, in looking at these, looking at this video, you'll be able to see like, oh, I could have done that. This admittedly is a very long problem. This last one, there could have been some shortcuts that you could have taken to really streamline the thing. But this is what I was looking for particle kinetics. So thanks, and let's have a conversation if you're not pleased with the results. Thank you.